everyone. So my name is Hana Boukharouba. I am a PhD student at the University of Paris Saclay. And today I am going to present you a high sensitivity multifrequency inductive sensor used for the non-contact monitoring of kiwifruit ripening. As you may know, the assessment of fruit quality is a significant concern across the entire fruit supply chain. It is important in order to meet with the consumers' needs and their preferences. During ripening, fruits like kiwi fruit undergo physical and chemical changes that can be assessed in subjective ways through our senses. So to objectively assess these changes, the agri-food industry has developed some techniques, but these techniques are mostly invasive, destructive, and sometimes expensive. And that's why today we will, in this presentation, we will investigate an electromagnetic inductive technique, which is non-destructive, low-cost, and easy to implement. So the basic principle of this technique is as follows. First, when current flows in the monitoring probe, it induces a magnetic field that is amplified by passive resonators and propagates in my kiwi fruit. So this magnetic field interacts with the electric property of the kiwi fruit. It is already known that the electric properties as a relevant indicator of the physical and chemical change of organic matter especially in the radio frequency range. So this the electric properties can be measured by the complex permittivity, which is related to the relative permittivity and to the electric conductivity. So the sensor in question is a resonator based on circular transmission lines. It is constituted of two copper tracks that are deposited on a dielectric substrate. It is distantly activated at certain frequency and through an inductive coupling with the radio frequency probe, and which is made from a wire loop coil and connected to a vector network analyzer. So the frequency, the resonance frequency of this resonator and its electrical elements and quality factor are determined by its geometry. So it depends on the diameter, the thickness, and the width of the copper tracks and the thickness of the substrate. So with this kind of configuration, we can get one information at one frequency. So since these transmission lines can feature different geometry, the idea was to combine several geometries on one configuration in order to have what we call the wireless multifrequency resonator that can be able to give more information at different frequencies. So the configuration that I will present in this study will be detailed in the next slide. So here we have a configuration constituted of 3 transmission line resonators with different diameters. So the resonance frequency of each one and its quality factor are summarized in this table. So the resonance frequency can be determined either analytically or in a load-free configuration, as shown here. The spectrum of the measured impedance shows three different frequencies which correspond to the frequencies of my resonators. And this sensor can be modeled with an equivalent electrical circuit as shown here, which which is composed of a RL mesh for the RF probe and 3 RLC meshes, which correspond to each resonator. And here, in the presence of my Kiwifruit, additional elements RK and LK, which are related to my Kiwifruit, are added to each RLC mesh. As a result, the complex impedance of my electrical equivalent circuit can be written as follows. At each resonance frequency, so the elements RK, LK are in my model are to be are estimated for each frequency, where RK models the losses of energy in my Kiwifruit, and the LK models the storage of energy fruit, which are the first one is related to the conductivity, and the storage of energy in of LK is related to the related permittivity. So it's to evaluate the capacity of my sensor to monitor the ripening of the Kiwifruit, we decided to conduct a study over 14 days, where I took 2 Kiwifruit with the same characteristic, and the first day, the 2 Kiwifruits have undergone a mechanical stress, and the reaction force was recorded. After that, the Kiwi number 1 was dedicated for the electromagnetic characterization, and the electric properties were recorded each day. And on the other hand, the Kiwifruit number 2 was dedicated to the mechanical tests, and the reaction force of the Kiwifruit was recorded by the force sensor each day also. The results of these 2 methods will be discussed later. So the electromagnetic characterization is done as follows. First, we plot the measured data by the vector network analyzer around the frequency F1. After that, we adjust the sensor model expressed by this equation. We're using a complex minimization algorithm which fits the model data to the experimental data. And here we can estimate the values of RK and LK for the frequency F1. Once this operation is done, we repeat the same thing for F2 and F3. At the end, we have the 6 parameters that correspond to my 3 frequencies. So if we implement this measurement method each day during 14 days, we obtain the results here. So on the left, I have the estimation of the induced resistance for each resonator during days, and on the right, I have the evolution of the induced inductances for each resonator during days. So as you can see here, we have an increase of these parameters that can be associated with the ripening of the fruit. And we add also a third parameter, which is ROK, which is defined by the ratio of the real part on the imaginary part of the equivalent impedance. This parameter is can be considered as a loss factor, and it indicates the structural change within the fruit. As you can see here, for each frequency, we have a monotonous decrease of this parameter during days, which can be related to the change in the structure of the fruit while ripening. And we also can plot the spectrum of this of this factor function of the resonance frequency. And here and this spectrum shows a significant change of the Kiwi function of frequency, and this can be related to the ripening of the fruit and to the different stage of maturation. So to compare these results with the mechanical characterization, here we have we plot the reaction force of the kiwi fruit during days. So as you can see here, we have a significant decrease of the reaction force of the kiwi fruit number 2, which can be validate that our kiwi fruit is losing its firmness, which confirms the visual aspect and the electromagnetic characterization. And to conclude, we have proposed a novel multi-frequency sensor, which is sensitive to both to the relative permittivity and to the conductivity. It is able to monitor the ripening of fruit in a non-contact and non-invasive way. These promising results open the way to low-cost and non-invasive application in the agri-food industry, and also it paves the way to the application of this kind of technology in the field of healthcare and biomedical application. Thank you for your attention, and